to talk about the paper in which Juan Neirotti written about consensus formation times in anisotropic societies. The anisotropic characteristic is concerned by the equal distributed opinion in the initial time on the hypersphere of agents. So in the initial time, all the people on our society has a random opinion. So it's not a polarized society. Okay, so first I'm gonna talk about the model. So there is a mechanism for the agents to assimilate information and update their opinions. So basically, we're gonna use Bayesian actualization, but we're gonna make some thermodynamics approach to this model, okay? The model considers the existence of a set of rules B that determines what is socially acceptable. This field B can be interpreted as a government or absolutist that that makes his opinion over the population, okay? Imposes his opinion on the population, okay? The model considers the interaction of the agents with their neighbors. Eta equal for all pair of agents. So we're gonna make a topology in which the interaction of the agents are equally have equal intensity, okay? So eta is constant. So first I'm gonna introduce some variables. So we have a set of questions, zeta. So zeta is a question in which the agent has an opinion. So we're gonna introduce the variable sigma A is the opinion of the agent A, and sigma A is equal to the signal of the synaptic vector JA, scalar to the question, okay? And the opinion of the government is sigma B, and it's analogous defined, okay? So they are binary variables. They assume values -1 or 1, okay? So now we are concerned in to make statistical mechanics of these models. So we're gonna show an Hamiltonian that describes our system. So this Hamiltonian has a term that evaluates the opinion of the agent compared to the opinion of the field. Also, they have a component that evaluated the opinion of two different agents. And we're gonna use this expression to evaluate the energy of the system, okay? So now our task is to study the thermodynamics of the system and this Hamilton to find phase transitions and interpret these results. So it's interesting to look at the free energy of this Hamiltonian. So first, I'm gonna review what partition function is. So the partition function is simple, the sum over all possible states of the exponential of beta h. So beta is the inverse of the temperature, can be interpreted as a Lagrange multiplier. So that's a constraint that maximizes the entropy and the information of the system. So so the partition function is the sum. And now we're gonna use a smart trick to evaluate the average of the system. We are in a Kenshet disorder, so we are looking for average And the average of z to a power of n is easier to evaluate it comparing to the average of log z. So we're gonna use a replica trick with consists in the application of this limit. This limit log z is equal to limit this limit. So we gonna do average over sorry, the free energy is proportional to the log z. So interesting, we're looking to average over the free energy, so we're looking to average of log z, and we're gonna use this expression to simplify our average, doing the average over the z to the power of n. Okay, so our task to evaluate the free energy is simplified by found the average of z to the power of n. So this is a smart trick that will make more easy our goal. So putting our Hamiltonian in this expression for the partition function, we have this expression here. So now our goal now is to evaluate these sums, and that's not too easy, but let's try, okay? So first, we are interested in the average over the questions, zeta, the field B, and the synaptic vectors. So this average can be substituted by simply by multiplication the probability densities of each one of these variables. So we're gonna assume that the issues are Bernoulli variables that has probability 0.5 to be +1 or -1. So this probability density probability is a delta, and our field we're gonna assume that he's uniform on the sphere in a direction k, so the probability distribution is simply a delta too, and we're gonna assume that our society is anisotropic, so the synaptic vectors are uniformly distributed on the hypersphere. So the distribution of probability to have a vector j is simply a delta 2. So we have a lot of deltas, and we're gonna substitute this average by 3 deltas, and we're gonna expand these deltas on the representations of the Fourier space of the delta. So we are gonna introduce some Fourier variables and some new integrals, and we have these expressions. So our task now is to evaluate these integrals. It's not too easy. We're gonna make a lot of approximations, but let's go. The next step is to introduce a lot of new variables that will simplify our calculation. We're gonna introduce this RA gamma, which is the overlap of the synaptic vector of one replica. Gamma index is related to the replica partition function. So we're gonna average different replicas. So this explanation is related to that. And okay, W is the overlap of two different synaptic vectors of the same replica, but at different agents. So we have two different agents of different replica. This is the overlap. Q is the overlap of the same agent in different replicas, and T is the overlap of different agents in different replicas. Let's go back a little. When I said replica, I mean, when I'm doing this average, I'm saying that I can study the system like averaging and equal replicas. So I'm doing some average of replicated system. This is a property of this trick, and this is useful. So I'm gonna define some matrix to evaluate our calculations. Okay, I'm not going to waste too much time on the calculations, but I will do some algebra here. So substituting these new variables at our expression of the partial function, we now have these integrals to be solved. And look at this n. We are interested in thermodynamics, so we're gonna take the thermodynamic limits in future. So we can use Laplace method of approximation, Laplace method to approximate this integral. So the terms that contributes more to this integral is the minimum of GS. So here we have GS, that is an entropic contribution to the free energy, and here we have GE, it's energetic part of free energy, and we have this integral. So our task is to evaluate this integral, but we gonna use some approximations. So first I will use the Laplace method. So in large n limits, we can apply the Laplace method to solve integrals over K and R. The Laplace method consists in we find the critical points that minimize this expression. So deriving GS and equalizing to 0, we have these relationships in which minimizes GS. We're gonna use this notation. X trace is basically the same integral, but substituting the point that minimizes the exponential. So this is just a simple notation. So evaluating and finding the minimal points, we can substitute to our function and find that the entropic contribution is k, which is a new variable that I introduced here, k to the power of n over 2. So our task now is concerned to find the energetic part, which is not easy. So we have to solve this integral now, and it's a little bit difficult. Well, to evaluate the value of k, I'm gonna impose an ansatz. This is an ansatz. I'm gonna say that the replicas are symmetric. So I will impose that the R of different replicas needs to be the same. So all the replicas have the same opinion. The agent A of the replicas have the same opinion, and I will make this over all the variables. So the replica are symmetric. This is an ansatz to our solution, but doing that, we can make much easier the evaluation of the calculation. So we're gonna substitute now our ansatz, and we will find that the entropic contribution is equal to this. Okay. Look, I'm saying that this product can be can be approximated to 0. This I will not prove. There is a paper that proves this relationship. If someone are interested in it, I can send So, but okay, we use this scaling property. And now I'm going to evaluate the second integral. Okay. So I think that I make it too fast, so I will recapitulate all that I did. Okay, so the problem is we have agents, we have questions, and we have a rule. Okay, so the rule is a government or a status quo. So the rule have an opinion over the questions. So the questions eta, okay, and the agent has an opinion to this question too. And this Hamilton implies that this term contributed says that the energy will be minimal when two agents have the same opinion. So if I have the same opinion with you, so the energy is negative, our contribution to energy is negative, and so this Hamilton is like can be similar as an Ising Hamilton, in which way that two spins tend to be aligned. So so this is the interpretation why we choose this Hamiltonian to model society, because people tend to agree with one with each other. So then I use some statistical mechanics approach, use this replica trick, and find these expressions. So let's continue. So now our goal is to evaluate the energetic contribution of the free energy, and we're gonna use some transformations here. We're gonna use Hubert-Sternovic transformation, which consists in evaluate an integral to reduce the power of the b term of the exponential. So this will simplify our calculations. So this integral gonna be introducing some new variables, Stanovic variables. We can reduce that integral to this, and now we're gonna use some approximations, also the Laplace method. And so our goal now is to study the minimum points of this function. And that's trivial because this is a quadratic polynomial. So analyzing the intervals and the minimization of the parabola, we have that the minimal is achieved when by this function, okay? So now we have the two contributions of the free energy. So we have the contribution of the entropic term and the energetic one. So now we can come back to our trick, because remember, we are concerned to evaluate the free energy proportional to log z, but we only evaluated the z to the power n. So now we're gonna take the limit to find the log z. So we're gonna apply the replica trick now. Sorry. We're gonna apply the replica trick. So here we go. We have that our free energy is proportional to this limit, and we're gonna take the limits, the thermodynamic limit, and evaluating this is simple doing the Laplace method again. So we're gonna we're going to minimize the entropic term and the energetic one. Well, the entropic term is this function, depends on Q. It is achieved the minimum when Q is equal 1. So this part is trivial to minimize. So the minimization of this first term does not depend of the variables R or W or alpha or beta. So the minimization of the free energy depends only in the minimization of this term. So our goal now is to minimize this potential. So we're gonna make derivatives and equalize to 0. And doing that, we're gonna straightforward find the state equations of our system. Finally, we have the state equations. So this is like your state equations is like the space equation in mechanics, is like okay, is the function, the equation in which we are interested to solve. So of course we cannot solve this analytical, so we're gonna use some numerical approach. And doing the numerical approach, we finally can find the phase space. So here is the phase space, and now we gonna interpret this. So H0 is the interaction between the agents. So in this axis is proportional to the H0, and here is beta, which is related to the temperature. So we can see that if the interaction of the agents are too big, we have that the agents are against the status quo. So if we talk a lot, if we change opinions a lot, if we interact a lot, and if all the society does the same, is more likely that the society rebel against the status quo or the absolutists. But if the society do not interact sufficient, so if H0 is low, the society establish in favor of the status quo. So here we can see if we have to do a revolution, we need to interact with all the people. We have to have a strong interaction one with each other. So we can see here a phase transition, which can be interpreted in an absolutist context as a revolution. So here we can see the phase transition. So this region is a region that the agents do not have a clear opinion. So it's like a disordinate state, like disordinate spin state. And we see that conforming the interaction are increasing, this region is less likely to happen. So and this region happens in high temperatures. So well, this agrees with our intuition of spin theory. And finally, this is our space phase. Well, now we can discuss the validity of the model, and we also can stipulate this model to some new cases. In my personal my personal interest, I'm doing a research to try to add to this Hamiltonian love factor, like like Machiavelli said, you need to be afraid and you need to be loved to manipulate your population. So I'm trying to add to this Hamiltonian love contribution, and I will try to find data of absolutist societies and try to conclude if it's better to be loved or it's better to be afraid. But we can extrapolate this to a lot of situations and models. It's a pretty cool method to study society. So that's it. And if someone wants to say something or to ask something, it's I think that I went too fast. Yeah, I went too fast. Well, there are questions. No questions?
I guess maybe since there's no more questions, you would like to say something else, Jose? And I'll stop the recording.
I want to say sorry because I thought that the seminar was too big, so I just improved my step, so I go fast and fast, thinking that I will not have time, but I did it in half hour. So I just want to say sorry to go so fast. So
no problem. I have the same problem with my seminar too.
but that's it.
Well, I'd like to ask a question.
Okay.
Sorry, I came late, and I reached it out when you are already on that last slide. Is this R equals to 0 region? Is it something like the paramagnetic phase of a
It's like a disordered magnetic. It's not the magnet. This region we equal to 1 is like spin up region. All the spins are +1. This region, all spins are -1. This is a chaotic region where the system are disordinated. So it's similar to phase transitions in spin lattice. But here we apply our model of spins to societies. But it's analogous.
That's really cool. I thought the R equals to -1 was something like a spin glass phase, you know?
Yeah.
But it's antiferromagnetic.
Yes, it's like that. It's like that. The spins are against the status quo. Yeah, it's similar. Yes.
Really nice, Jose. Congratulations.
Thanks. But there are a lot of extensions that this model can have. We can add another terms. We can manage this Hamilton to add some characteristic. We can do the calculations in an isotropic societies, like with in initial phase, the synaptic vectors are oriented. So we can, for example, here when I suppose that the synaptic vectors are uniformly distributed to one direction. we can make this not too uniform, like we can say polarized society, and we can see how a change can, how we can change the opinion of the society, and we can do thermodynamics with that. So it's interesting. I think it is interesting.
Oh, that's really interesting. I love string models too. Are you using like a replica symmetric mean field theory?
Yeah. I impose in the we imposed in this paper the symmetric replica, this symmetry in our replica. So here, where is the step? So in this here in this part of the seminar, I impose that all the agents of all the overlaps of the agents A with the opinion B in different replicas are the same. So the different replicas have the same overlap of agent A. This is an approximation in the ansatz. Sometimes these get wrong, and we have some thermodynamics anomalies like negative entropy and something like that. But we can study, and we can check if that it's right, okay? But it's not the scope of this presentation. I just assume this and I proceed with the calculation. So yeah.
Really nice. And my last question, are the interactions between different agents essentially positive?
Yeah. I assume that the interaction of different agents are the same and are positive. Yes, yeah. Yes, they are positive.
Do you know how it behaves when you have like glass interactions, mixed positive and negative interactions?
That can be an interesting case. Like, you mean like I do not like you, so if you have opinion +1, I will have opinion -1. Yeah, that's a cool scenario. I think there's a scenario like that in which some people of my research team did it, but they did it with simulations in which each agent is a perceptron and has a extra term on the vector of the perceptron that is the trust. So we have the matrix, one matrix that relates each agent trust in which other. So if I don't trust you, I will tend to align my spin in the other direction against yours. So you can study the dynamics of the societies, but it's a different model. Yeah, I think they did some analytical calculations. I don't know now, but computational calculation, I'm sure they did. It's pretty nice. They compare, and then they use this model to evaluate, to compare the decision of American court of the I forget how can I say juiz in English, referee. Yeah. So it is the term referee used to law judgments. I don't know, but yeah, they compare their model with the results of the American Court of Judgment, and they have pretty nice results with that. It's a nice paper, and it's yeah, I think that this is interesting, but there are
well, I found it really interesting too, José. Thank you very much.
You're welcome.
Well, anyone has any more questions, commentary, anything you would like to add? Well, so we will end the recording here. And I would like to thank you everybody for being here for this seminar. And thank you especially to José for presenting to us.